This is Lecture 6 of our Canopy Analysis and Design under Wind Load. In Lecture 5, we completed the analysis of the open canopy portion. In this session, we shift our focus to the enclosed sections. Here, our goal is to determine the wind loads acting on a typical frame located within these enclosed spaces. There are 3 enclosures beneath the canopy. 2 are identical in size, while the one on the left is wider. Let's begin with the dimensions. The wider enclosure measures 40 meters long, 5 meters wide, and 8 meters tall. It has 2 openings, one in the side wall measuring 2.1 by 1 meters, and another in the back wall measuring 2.1 by 1.8 meters. The smaller enclosures each measure 16 by 5 by 8 meters. Each of them includes a pair of doors, one on each side wall, measuring 2.1 by 1 meters. Importantly, there are no other doors, windows, or roof openings in any of the 3 enclosures. According to ASCE 722, buildings are classified into 4 categories when evaluating wind pressures: enclosed, open, partially enclosed, and partially open. Let's start by examining the smaller enclosures. A building qualifies as enclosed if the area of openings in any wall that receives positive external wind pressure is less than or equal to 1% of that wall's area, or 0.37 square meters, whichever is smaller. For the smaller buildings, the wall facing the wind, either the front or the back, is 16 by 8 meters, totaling 128 square meters. 1% of that is 1.28, so the governing threshold is 0.37 square meters. Since the front and back walls have no openings, all doors are in the side walls, the area of openings in the positively pressurized wall is 0. That means the smaller enclosures clearly meet the criteria for being classified as enclosed. Now, let's turn to the wider building. This structure has an opening in the back wall, which receives positive pressure when the wind blows from north to south. The area of this opening is 2.1 by 1.8, which equals 3.78 square meters. The back wall measures 40 by 8 meters, that is 320 square meters. 1% of that is 3.2 square meters, so again the limit is 0.37. Because 3.78 exceeds this threshold, the building does not qualify as enclosed under north to south winds. However, when the wind direction reverses, blowing from south to north, the front wall becomes the positively pressurized surface. That wall has no openings. So in that case, the building does qualify as enclosed. In summary, the classification for the wider building depends on wind direction. For south to north wind, it is enclosed. For north to south wind, it does not meet the criteria for enclosed. So what's the correct classification under north to south wind? Could it be considered open? ASCE defines an open building as one in which each wall is at least 80% open. Clearly this doesn't apply. The front wall has no openings, and the back wall has only 3.78 square meters of openings, far less than 80% of its 320 square meters. So how about partially enclosed? ASCE requires that 2 conditions be met for this classification. 1. The area of openings in the positively pressurized wall must exceed the sum of openings in the rest of the building envelope by more than 10%. 2. The same opening must also exceed 0.37 square meters or 1% of that wall's area, and the percentage of openings in the remaining building envelope must not exceed 20%. Let's walk through the numbers. The opening in the back wall is 3.78 square meters. The only other opening is a 2.1 square meter door in the side wall. 10% of 2.1 is 0.21, so the back wall opening must exceed 2.31 square meters. Since 3.78 is greater than 2.31, the first condition is met. For the second condition, as we established, 0.37 square meters is the governing threshold, and 3.78 clearly exceeds that. The total area of the other three walls, two sides at 5 by 8 and the front wall at 40 by 8, is 400 square meters. The only opening in these walls is 2.1 square meters, which is just 0.53% of 400, well below the 20% limit. So, both conditions are satisfied. Therefore, the wider building is classified as partially enclosed when the wind blows from north to south.
In summary, we must account for 3 enclosure classification scenarios to determine the critical wind effect on a typical frame within the enclosed portions of the bus terminal. For the 2 smaller enclosures, classification is straightforward. They are considered enclosed under all wind directions. For the wider enclosure, the classification depends on wind direction. When the wind blows from south to north, the enclosure qualifies as enclosed. When the wind blows from north to south, it is classified as partially enclosed. This distinction will guide our selection of the appropriate wind load cases in the upcoming analysis.
This classification directly affects the wind pressure equation, equation 27.3-1. In this equation, the internal pressure coefficient, GCPI, depends on whether the building is classified as enclosed or partially enclosed. For enclosed buildings, internal pressure effects are small. But for partially enclosed buildings, large openings allow wind to pressurize the interior much more, resulting in significantly larger internal pressures. This difference can greatly influence the net wind pressures acting on the frame, which is why getting the enclosure classification right is important. For a flat-roofed building like ours, we have 5 external surfaces, as shown in this diagram. To calculate the external pressures acting on these surfaces, we need to determine the pressure coefficient, Cp. The other terms in the equation are already known. For enclosed and partially enclosed buildings, ASCE figure 27.3-1 gives the external pressure coefficients. The figure also shows how wind loads are distributed across each part of the building envelope. On the leeward wall, the wind pressure remains constant from top to bottom. It is a uniform load. On the windward wall, the pressure varies with height, increasing as we move up the wall. For the side walls, the wind load is again uniform, similar to the leeward wall. At the roof, we apply a segmented uniform load across the top surface. And because our roof includes overhangs, we also consider a uniform pressure acting on the bottom surface of each overhang. With that in mind, let's proceed to determine the wind pressure coefficients and the corresponding pressures for these surfaces. We begin with the leeward wall and the side walls, since they share the same load pattern. The pressure on the leeward wall is calculated using the velocity pressure at the roof level, QH, the directionality factor, KD, the gust effect factor, G, and the pressure coefficient, Cp. Back in Lecture 3, we determined the velocity pressure, It equals 1,179 newtons per square meter. The directionality factor and the gust effect factor were established in Lecture 4. To determine CP, we refer to Figure 27.3-1 of ASCE 722. As shown in the figure, CP for the leeward wall depends on the L over B ratio, where L is the length of the building in the direction of the wind, and B is the width of the building measured perpendicular to the wind. For the smaller enclosures, L is 5 meters and B is 16 meters. This gives us an L over B ratio of 0.31. According to the figure for this ratio, CP equals negative 0.5. Therefore, the wind pressure acting on the leeward side of the smaller bus terminal enclosures is negative 426 newtons per square meter. The negative sign indicates that this pressure force acts away from the wall. It's a suction effect. We can determine the wind pressure on the sidewalls in the same way. Except for C sub P, everything else remains the same. The velocity pressure at the mean roof height, QH, is 1,179 newtons per square meter, and both KD and G are 0.85. To determine CP, we once again refer to Figure 27.3-1. According to the figure, CP for the sidewalls is negative 0.7, and this value applies for all L over B ratios. This gives us a wind pressure of negative 596 newtons per square meter on the side walls. Similar to the leeward side, this is a suction pressure. The force acts away from the wall. The wind pressure on the windward side of the building varies with height. It changes as a function of the distance from the ground, z. We refer to the wind velocity pressure at height z as qz. The directionality factor, kd, and the gust effect factor, g, are the same as before, both equal to 0.85. To determine the wind pressure profile on the windward side, we first need the expression for Qz. We discussed this equation back in Lectures 2 and 3. In this equation, Kz is the wind exposure coefficient, which varies with height z. We established the equation for Kz in Lecture 3. Kzt is the topographic factor. For our building, this equals 1. Ke is the ground elevation factor, which is also 1. And v is the basic wind speed, which we previously determined to be 45 meters per second. With these values in place, we can now write the complete equation for the wind pressure acting on the windward side of the building. The pressure coefficient, C sub P, for the windward wall is given in Table 27.3-1. It equals 0.8. So, the wind pressure equation simplifies to. There's one more detail we need to take care of. According to ASCE Table 2610-1, for heights less than 4.6 meters, the velocity pressure coefficient is to be calculated as if the height were 4.6 meters. In our case, as we discussed in Lecture 3, Zg and alpha are 750 and 9.8 respectively. This results in a constant wind pressure of 611 newtons per square meter for the lower 4.6 meters of the wall. Above this, the equation gives a non-linear pressure distribution for the upper portion of the wall. Given that the building height is 8 meters, this non-linear portion applies only to the top 3.4 meters of the wall. The calculated pressure at the top, at Z equals 8, is 681 newtons per square meter. So here is the overall shape of the pressure distribution on the windward side of the building. Now, since this nonlinear pressure profile would make the structural analysis more complicated, we can conservatively approximate it using a rectangular pattern. So, this is the windward wall pressure distribution we'll be using in the frame analysis. Here is a summary of the wall pressures we have determined so far. On the leeward wall, there is a suction pressure of 426 newtons per square meter. On the windward wall, the pressure is segmented. In the lower portion of the wall, the pressure is 611 newtons per square meter. This increases to 681 newtons per square meter in the upper portion. And each sidewall is subjected to a suction pressure of 596 newtons per square meter. Now, let's turn our attention to the roof pressure. Note the ratio of H over L. It equals 0.32. When this ratio is less than or equal to 0.5, ASCE Figure 27.3-1 defines 4 pressure zones for the roof. We'll label them Zones 1 through 4. Zone 1 covers the portion of the roof within a distance of H over 2 from the windward edge. In our case, since H is 8 meters, Zone 1 extends 4 meters from the windward edge. Zone 2 also has a width of H over 2, another 4 meters, immediately following Zone 1. Zone 3 covers a width of H, that's 8 meters for our building. Zone 4 covers any remaining portion of the roof beyond Zone 3. In our case, this distance is 9 meters. According to Figure 27.3-1, we need to consider 2 pressure coefficients for each zone. Since there are 4 zones and 2 pressure options per zone, this results in a total of 16 roof pressure patterns. The pressure coefficient patterns can be tabulated like this. When we substitute these coefficients into the expression for external pressure, we obtain the external pressure patterns for the roof. It's important to remember that the pressures we've calculated so far represent only the first term of the wind pressure equation. We still need to determine the second term, the contribution from internal pressure. Let's do that now. Table 26.13-1 provides internal pressure coefficient values for enclosed, partially enclosed, open, and partially open buildings. Since our building is enclosed, we use an internal pressure coefficient of plus or minus 0.18. A positive value indicates pressure acting toward the interior surfaces, while a negative value represents pressure acting away from the interior surfaces. When combined with the external pressures, the combination that results in the most critical bending moment in the frame will govern the design. The internal pressure term in the wind pressure equation is, according to ASCE Section 27.3, page 282, for the windward wall, side walls, leeward wall, and roof of an enclosed building, the internal velocity pressure, QI, is taken to be equal to QH. In our case, that means QI equals 1,179 newtons per square meter. The wind directionality factor, KD, is 0.85. Using the internal pressure coefficient of plus or minus 0.18, we calculate the 2 possible internal pressures. Now, let's combine these internal pressures with the external pressures we previously calculated. For the leeward wall, the external pressure is 426 newtons per square meter, acting away from the wall. This is considered a negative pressure, since positive pressure always acts toward the surface. So, because the pressure is pulling away from the wall, we describe it as negative. Now, we need to consider two internal pressure cases, one positive and one negative, which gives us two scenarios, labeled A and B. In scenario A, the internal pressure is positive. This means both the external and internal pressures are acting in the same direction. As a result, the total pressure becomes the sum of the two, negative 606 newtons per square meter. In scenario B, the internal pressure is negative. In this case, the external and internal pressures act in opposite directions, so they partially cancel out. The total pressure on the wall, therefore, becomes negative 246 newtons per square meter. For the side walls, scenario A amplifies the suction pressure. The internal pressure acts in the same direction as the external pressure, increasing the total effect. In scenario B, the internal pressure opposes the external pressure, which reduces the total suction. In other words, it dampens the pressure on the wall. For the windward wall, in scenario A, the internal pressure opposes the external pressure, which reduces the total pressure on the wall. In scenario B, however, the two pressures act in the same direction, so the total pressure on the wall gets amplified. To determine the total pressure on the roof, we need to keep in mind that it consists of 4 pressure zones. For south to north wind, zones 1 and 2 are located above the long roof overhang. Because of that, they are not affected by internal pressure, which only develops inside the building envelope. Zone 3 is also mostly positioned over the overhang. The combined width of zones 1 through 3 is 16 meters, which is 1 meter more than the length of the overhang. To simplify the analysis, we'll adjust the width of zone 3 to 7 meters, so that it lies entirely over the overhang. As a result, we need to adjust the width of zone 4 to 10 meters. This zone spans both the portion of the roof that is above the enclosed space and the remaining short overhang. To account for this, we divide zone 4 into 2 parts, zone 4A and zone 4B. Zone 4A lies over the enclosed portion of the building and is subject to internal pressure. Zone 4B, located over the short overhang, is not affected by internal pressure. Since internal pressure only acts in Zone 4A, the total pressure in Zones 1 through 3 and Zone 4B is simply the external pressure for that zone. For Zone 4A, however, the total pressure is the sum of the external and internal pressures. We previously determined that there are 16 external roof pressure patterns to consider. For each of those patterns, we need to evaluate 2 internal pressure scenarios. Scenario A, where the internal pressure in Zone 4A is positive, and Scenario B, where the internal pressure is negative. This gives us a total of 32 roof load cases. For the sake of brevity, I mention only 4 of these cases in this lecture. The rest are provided in a downloadable text file. As examples, we'll look at Pattern 1 and Pattern 8. For each pattern, we'll consider 2 scenarios. Scenario A, where the internal pressure is positive, and Scenario B, where it is negative. Pattern 1 of the external wind pressure on the roof consists of a uniform pressure across all 4 zones. When we add the positive internal pressure in Zone 4A, the total pressure in that zone increases, since both pressures act in the same direction. However, when the negative internal pressure is added to the external pressure in Zone 4A, the direction of the total pressure reverses and its magnitude decreases. As we will see later in the course, these different load patterns have distinct effects on the bending moment in the roof beams. One pattern reduces the positive moment, while the other amplifies it. Now, let's examine pattern 8 of the external roof wind pressure, combined with the two internal pressure scenarios. In Zone 4A, the external pressure is a suction pressure of 256 newtons per square meter. When we add the positive internal pressure, the total uplift pressure in this zone increases to 436 newtons per square meter. On the other hand, when we add the negative internal pressure, the uplift pressure is reduced, resulting in a total of 76 newtons per square meter in Zone 4A. We're almost done with the wind load analysis for the smaller enclosures of the bus terminal. So far, we've determined the wall and roof pressures using ASCE section 27.3. However, this section does not account for the pressure that can develop beneath the roof in the overhang areas. Our building has two overhangs, one long and one short. Section 27.3 focuses on suction pressure on the top surface of the roof, but it does not address the pressure acting on the underside of the open overhangs. So we now need to determine those pressures and include them in our analysis. Let's take a few minutes to account for these under the overhang pressures before we wrap up the lecture. On both the windward and leeward sides, the pressure beneath the overhang is taken to be the same as the external pressure on the adjacent wall. So, for the windward direction, we apply a uniformly distributed pressure of 681 newtons per square meter, acting upward. This is the same as the external pressure we previously determined for the upper portion of the windward wall. On the leeward side, the external wall pressure is 426 newtons per square meter, which results in a uniform downward pressure of the same magnitude under the overhang. Based on this, we now need to update the roof pressure profile accordingly. That means we'll add these under overhang pressures to zones 1, 2, 3, and 4B, based on their position relative to the overhangs. Specifically, for pattern 1, both scenario A and scenario B should now include the under overhang pressures in their total roof pressure distribution. This gives us an updated pressure profile for those cases. We'll need to apply the same adjustment to the remaining load patterns as well. The complete list of updated wind pressure scenarios is available for download. In the next lecture, we'll convert the wall and roof pressures into loads acting on a typical interior frame.